It's a great thing that we're all together, and for the first time you will have the opportunity to present your projects. The idea was to have a physical meeting. Unfortunately, due to the COVID, we couldn't organize that from the beginning. But let's hope that in the future, we will meet in person at a physical event. So even after this meeting, we can stay in touch and help each other and keep the network and the momentum that we have. So we can arrange to meet physically in a next meeting. So our goal as an I-NERGY project was to reinforce the service layer of AI and demand platform in the AI energy sector, and to get a lot of use cases on how AI can be beneficial for the energy sector in a wide range of energy stakeholders, ranging from TSOs, DSOs, energy service companies, and as well as stakeholders that have to do with energy efficiency and relevant energies, and lay the foundation for the AI research innovation for the energy ecosystem. But our goal was always beyond the competitiveness of the SMEs. It's also the AI proliferation in the energy sector has a great premise for a larger environmental and social impact, and it can help for the decentralization, the democratization, and digitalization of energy, for the environmental sustainability, to alleviate the energy poverty and fight along other forces for preventing climate change and environmental degradations. So the first technology program has ended, as you all know. It was targeted to SMEs and startups. We had 10 winning projects that joined the 6-month technology transfer program that started at the end of April 2022, and it was rewarded 50,000 euros for the beneficiary. And the idea was to develop building blocks and applications for new AI algorithms and services to address challenges within the energy sector and to enhance the European sane AI on demand platform. So today, you will have the opportunity to see these AI building blocks and applications that the new winning teams have. And you will see the results of our journey. We are very happy to see each and everyone's contributions. Everyone did a great job. But the journey doesn't end here. We have a second open call that Thomas will currently let us know of more information about it. So Thomas.
Okay, let me quickly share my screen with you. Just a second. I hope I'm sharing my screen.
Yes, we can see it.
Okay, great. So yeah, thank you and welcome everyone. Of course, today is more for the Technology Transfer Program 1 beneficiaries, so they can showcase what they have actually developed. But of course, as Spiros already has mentioned now, this is I-NERGY carries on, and there's a certain continuity here. So the second open call is also interesting for the beneficiaries. We just wanted to remind you about that as well, because actually you get some extra points if you have participated in the first round. So this is also very interesting for you and for all the other attendees today here to the final event. Yeah, we wanted to use the occasion of this final event. On the one hand, if you are interested in applying to the second open call, to see the results of the first round that hopefully can inspire you and give you a little bit more of context. Yeah, and then very quickly tell you about the second open call, which is currently running. As you can see here, it launched on the 10th of October and will finish on the 12th of December. And yeah, so these are the two open calls. I'm talking about the second one. As you can see here, who can apply? We just wanted to quickly run through that with you. On the one hand, as an SME, which could be a startup, as a service developer or provider. So actually the organization that creates the code that develops the technical element. And then the second member of the consortium, pilot infrastructure provider or a data owner, which could be any entity really that helps you, that provides the data to feed your models, which could even be a client of yours. For example, if you are already working in that with them. Here, the scope would be developing new services on top of existing technologies. So MVPs. In the first round, there were prototypes, which you will see in a minute. Here you will be developing MVPs. We're looking for 15 applicants, 15 solutions to be selected, and they can get up to 100,000 euros during a support program like the one that we had, a little bit longer, 9 months. So with mentoring and additional support. So this is the second open call. I think I will not go further into detail here because, as you will see in a second, we have a webinar and we have plenty of information for you on the website itself. So let me jump quickly here. If you are interested in the open call, there's a microsite. You have the URL here, I-NERGY2OCfundingbox.com. And on that website, you will see if you click the apply button, it will take you to an application form where you can write your application following certain questions. And to support you with information, you have at the top different tabs. On the one hand, you have a help desk where you can reach us. You have a community where you can sign up for. There's also a help desk room and other rooms where you can actually speak to your peers and maybe get more information. We have support documents for you, which I will show you in a second, and a quick description on how to apply. And since this is this second round goes about consortia, the two elements that I just explained to you, here you have a possibility to find a partner, giving your details or looking for organizations that have already given their details and then contacting them. So it's fairly simple and straightforward. So this would be the document tab. As you can see here, there's the guide for applicants. Please read it thoroughly. There's all the information that you need to apply is in here. We also have a frequently asked questions and a grant agreement template, which will just give you an idea what the agreement with us will look like if you get selected. Then here, this is the find a partner section. So as you can see here, present your organization. It's a simple questionnaire. You just quickly describe who you are and what you are doing, what you want to do in this open call. And here you have a section, see who is looking for partners, which is a simple database where you can see entities that have already filled in their information and that they are looking for a partner to create a consortium. You don't have to create a legal consortium just yet before having been selected. This can all be formalized if you get selected via the agreement with us. So to make it easier for you to create this, let's call it a partner rather than a consortium partner at this point. So this should be very simple and straightforward for you. And then how to apply, well, as you can see, it's just 6 easy steps: log in and sign up to access, click on the apply button, start a new application, fill out the application, submit the application. It's a very simple process. In any case, if you have further questions, we have 2 webinars. This is the first one that we are going to do. You can find this on the I-NERGY website, which is i-energy.eu, under news and events. And here you can sign up, register for this webinar for free. It's on the 17th of November at 11, and there we will explain in further detail elements of the open call, and have also a long Q&A section where you can ask your questions if we haven't been able to help you via the help desk and via all the documentation that I've just shown you. And here, just again, a quick reminder: please apply until the 12th of December. This is the microsite for the open call, and you can contact us via the help desk email or via the community, which has a help desk space as well. And I believe that's it. Thank you.
Thank you very much, Thomas. Thank you very much for the information. So let's get started with the presentations now, the interesting part. I will do a little bit of gatekeeping, so please try to keep it's 15 minutes along with questions. So I will give you a warning if you exceed this, so don't take it personally. It's just to be justice also to all the teams. So let's start with the first team, Adios.
Hi, Spiros. Hi, everyone. I share my screen in a second. Here we are. Can you see it?
Yes.
I am the project manager for Adios. That is the solution that we implemented. Basically, what we are doing is an high-performance anomaly detection tool that uses some latest techniques and machine learning to try to identify anomaly detection, usually using SCADA data. And is being tested and has been working with, we have been working with SCADA data on a substation power system. So basically what we have developed, what we have promised for the I-NERGY open call is a few things. First of all, developing, creating and sharing with within the IO for EU platform a SCADA open dataset with tagged anomalies, then develop a set of machine learning model for anomaly detection using this SCADA data, and also develop an application for anomaly detection. Then we have basically delivered a market and a commercialization plan analysis. We have further boosted our marketing strategy to basically market this platform and this system. And also we have published the asset in the catalog, and we have also created an experiment. So it has been an interesting journey for us. Especially, putting together this sort of infrastructure and architecture within, the I4EU catalog and experiment. But at the end of the day, 6 months, we were able to basically provide a solution, a working solution. In terms of the data set, and in terms of people, I have with me my chief data scientist, and I have my commercialization manager that will talk about quickly, about the data set, what we have used, and what we have done with this data. Cosimo, are you there?
Yeah, sure. Can you hear me?
Yeah, go ahead. Few minutes.
Hi, everyone. I'll try to be as as quick as possible. So a brief description of our dataset, which is composed of about 5 million samples representing the logs from an energy management system in the US. We were provided with about 2K of manually labeled alarms by a domain expert that divided the alarm into normal information, warning, and critical. So as we only dispose of about 2K labeled alarms on a dataset of 5 million, we first needed to come up with something to extend the set of labeled alarms, and this means to develop substantially a tagging system, which should be highly interpretable by even a non-expert user. So our approach is straightforward, meaning that it consists in tagging some of the unknown alarms with the same label of the most known ones. This is possible because each alarm can actually be represented as a set of features, and the distance between two alarms is simply counting the number of different fields that they present. We also enhance with this tagging system, including two state-of-the-art semi-supervised learning solutions, which are label propagation and label spreading. These methods leverage a graph-based approach, trying to cluster together on the same structure alarms with similar properties, and thus assigning them the same label. Our overall tagging system is a combination of our let's say, first tagging system together with this two graph-based approach, and using a voting system allow to obtain a noise-resilient tagging system, meaning that anomalies or strange alarms won't affect it. So, assuming to have a way to tag more alarms, we can then train our machine learning models. There are two, let's say, there are two ways to train our models. The first one is to use the selected features, the features automatically parsed by the people who generated the dataset. In general, these are categorical features, as you can read on the right side. So, for example, it's the source of the anomaly or the alarm, the equipment, the severity of the alarm, and so on. And hence, to employ machine learning on this, we must cast them into a one-atom encoding, which is a high-dimensional and very sparse way of representing the data. The other approach is different, meaning that it's based on the raw text, which was provided together with the alarms, meaning wasn't performed any parsing on this field. So we identify a vocabulary of meaningful words, which is VU, and for each alarm, we create a VU-dimensional vector that counts how many words in the alarm E are present with respect to VU. And in both cases, observe that these methods give birth to a very high-dimensional and sparse representation, which can be, let's say, harder to understand for a human rather than a machine learning algorithm. And that's the reason why we developed the earlier tagging system. This should be integrated into a feedback positive loop where the tagging system is interpretable. The user can understand and possibly correct it. And then this training step, based on sparse features, allows to provide a way to label a large set of alarms. So very briefly, the experiments, we measured the metrics, the metrics that we measured were the accuracy, and then the recall, the precision, and the F1 score on the critical alarms, which are the one that we are most interested in. And we substantially compare the behavior of three well-known machine learning algorithms, so logistic regression, K-means, and decision trees, comparing them when trained on categorical and on text-based features. And as you can see from the table, text-based features largely outperform the other approach.
Perfect. Thank you very much, Cosimo. So as you can see, we have now a machine learning pipeline, data pipeline. We have developed, an infrastructure that take into account, the experiment that we have done. At this point, what we have done, we start thinking how we can market this sort of system. And we have done a business model canvas. Dave is our commercialization officer that is here. And Dave?
Fabiano, thank you for that, and Cosimo as well. So I'm just going to give you a whistle-stop tour to our commercialization plan, which is demonstrated here through a business model canvas. And before doing so, great to talk to everybody this morning, to say the least. So I'll start with our headline, and that is obviously the objective of ADIOS, which has already, in fairness, been articulated by Fabiano, and it is to enhance power grid and renewable energy sources anomaly detection while contributing to power system stability and the integration of distributed RES, which is obviously critical given the current climate and energy crises. Now, at the center of our slide here is our value proposition. It's split in three between engineers, organizations, and consumers. So focusing first on engineers, it's about working with DSOs, TSOs, and engineers working with RES organizations, where our proposition brings enhanced situational awareness, crisis response, and better decision making. Secondly, with a focus on the DSO, TSO, and RES organizations themselves, it's where we facilitate early stage identification of faults and power line strains, allowing for the building of contingencies, increased power system stability, increased penetration of RES, as well as reducing the dispatch of peak generators. And then lastly, for consumers, which is arguably most important, it's about how our proposition lowers the risks of blackouts, and very important at the moment, it's about reducing the cost of service. So on the left and right of our slide here, you can see our partners and customers, many of which overlap, as you may see. So our initial focus is on DSOs and TSOs, such as eDistribución in Spain and EirGrid in Ireland. Partners also include industry organizations such as EDSO, the European Distribution System Operators Organization, and ENTSO-E. And then surrounding our value proposition in the center, those pieces surrounding the circle at the center, we've got key activities, relationships, resources, sales and marketing channels. And picking out a few items there, under key activities, we've included obviously our prototype development, including, as Fabiano mentioned earlier, our SCADA dataset. Under relationships, we've listed ease of use, ensuring, for example, we make the onboarding experience as efficient as possible. I'll move on quickly. Finally, and most importantly, we've got our revenue streams, which is outlined through our SaaS model. It's a monthly subscription fee with a setup fee and also professional fees. So that's a very quick whistle-stop tour of our commercialization model. Back to you, Fabiano.
Thank you very much. Thanks a million, Dave. And you can find a better and detailed analysis in the report. So in terms of KPI, as we have seen, we had, we have promised several KPI, three technical KPI that Cosimo basically explained, and we reached the target that we were proposed. In terms of business, we have created a market environmental analysis, thanks to David, a commercialization and pricing model for how we can basically commercialize this option. And also we have boosted our number of followers following the project and providing, advertising the project and the results. And also we have contributed to the A4EU platform. So we have reached all the KPI. If you go in the catalog, you can see, and you search for ADIOS, you can see 6 assets in the AI4EU catalog. I will not go into detail, but we have also the GitLab source code, thanks to the development team. And we have 3 assets published in the model for the experiment, and we have also prepared 1 experiment with the ACMOS platform. Just briefly, we were able also to create an MVP application and a sort of prototype application that you can find at this web address, where you can create with your data a sequential workflow from importing the data set to the label extension with the voting mechanism that we have developed, the training model, the import of the data set, the full data set, applying the model, and an analytics dashboard using the Grafana interface. We have also provided a public data set that is available for testing and is in the GitLab repository. And as soon as we will have access to the catalog, we will update the catalog to add the zip file for it. So just, if you didn't yet realize, here at IKIM, we have done this project ADIOS that stands for Anomaly Detection for Power Grid Operation Stability. And I'm Fabiano, and I developed, I conceptualized the project, but we are open for the second open call, but also for further collaboration. And you can find us in this LinkedIn page. So I think we are 12-13 minutes, so thank you very much to everyone. Are there any questions?
I don't see questions from the audience. Fabiano, you have done a great job, and thank you for all the contribution. A quick question for me, I don't know, it could be a big one, but what is anomaly for you? How do you define anomaly for your application?
Absolutely, Spiros, is a big question, in fairness, because if you see the literature, the anomaly usually is identified as a sort of a behavior that is outside the standard behavior of a system. However, in our case, an anomaly is a one alarm or a set of alarms that could lead to an intervention by a human being. So in the specific case of the public data set that we have shared, when we have a critical situation, so an anomaly is tagged as critical, it requires that if an operator go to the substation and check what is going on. So that's our definition of anomaly in this. But then from the literature is such a big, open, almost philosophical question, what is an anomaly? So I understand.
Yes, we
Thank you so much.
require a lot of hours to but thank you very much for specifying that. And again, many thanks for your great work and contribution. So let's go to the next presentation by AI for Demand.
Hello, everyone. Can you hear me?
Yes. Hi.
Okay, so good morning, everyone, and thanks, Spiros, for the presentation and for all your support during the whole implementation period of this project. And so I'm here representing Sensing and Control with our CEO, Narcis Avellana, and our project coordinator, Jose Saez. So I will share my screen. Just a second. Can you see my screen?
Yes, we can see it.
Okay, so I will shortly present you our the final results of our project called AI for Demand. So AI for Demand is about AI-based multi-layer tool for building energy consumption and demand prediction, which was implemented by Sensing and Control during the 6 months of the project implementation period. So the project's main objective was to develop a multi-level solution for short-term energy and consumption forecasting using the novel AI and statistical-based methods. The target of the analysis and prediction was selected the building level energy demand. And as a methodology, we chose cause and effect relationship analysis between energy demand and external factors. The implementation of the prediction module and the whole concept was done in Python environment with the help of novel data science and machine learning libraries. And our main and end goal was to contribute to an average reduction of 10% of energy consumption reduction through the improvement of demand prediction system accuracy, which will also result to the indirect reduction of CO2 emissions. So in shortly, I would like to present the methodology and the architecture of the main concept. So we applied hybridized methodology combining several data mining, statistical analysis, and machine learning techniques. And our architecture included 3 layers. So first of all, we had a data layer which was used to collect and store real-time data through the API services as well as IoT sensors. The next layer was the analysis layer, which presented the processing of all input data, including energy-related and weather-related data gathered from different sources, and the whole analysis of this data through the data pre-processing, feature selection, noise reduction techniques. And finally, the third layer presented the prediction layer, where we applied AI-based learning algorithms to train the relevant data sets and then forecast the future energy consumption and demand. So this is the main wireframe that we have implemented. And as you can see, as an input data, we used energy consumption and energy-related data, such as heat and cooling data, and together with weather-related information. Next, we used several data pre-processing techniques, for example, normalization, feature selection, and noise reduction techniques, where we have used random forest as a feature selection and discrete wavelet transform as noise reduction techniques. Next, in the prediction layer, we have compared 3 different machine learning models, which are LSTM autoencoders, LSTM, and random forest models to generate future forecasts of consumption and demand. And finally, to evaluate our results, we have used 2 evaluation metrics, mean squared error and prediction of change in direction to evaluate all the results. About experimental data, so for the evaluation of the prototype, we have used real-world energy consumption data obtained from the open source of City of Helsinki's Utility and Service Properties website. And we have used also meteorological data gathered from the Finnish Meteorological Institute's open data portal. The obtained research datasets included energy data collected from the buildings located in different parts of Helsinki, such as Malmi area, office building, and school building located in Kaisaniemi area. Different meteorological variables are gathered from 2 weather stations, which were situated closely to the buildings and the collected data included daily and hourly periodicity observations of these different energy variables and weather indicators. In total, we have used 7 and 11 variables to build our models. And as I said before, we have compared our freshly developed models with the 2 already developed models that we had already implemented in our product called N-Control. The first model was for a random forest-based model, and the second one was a bit complex model combining cross-correlation-based feature selection model with long short-term memory neural networks. And our last and final model was random forest-based feature selection model with discrete wavelet transform-based noise reduction and LSTM autoencoders model, combined model. The data sets were divided into training, testing, and validation sets, and all data sets were used 2 data sets were used to train and perform predictions for the comparative analysis. So here we have the results of the project. You can see that our lastly developed model outperforms the 2 other models, and here we can see Here we can see the best performing model against the real energy consumption data. And about project contributions, so we achieved, as an outcome, we achieved from 64 to 80% improvement in energy demand value prediction, and about 17 to 30% improvement in demand trend predictions. And as a final outcome, we wanted to have at least 10% energy saving through our demand prediction system, and our KPIs showed that we have around 14% energy saving and less emission calculated through the improvement of the average prediction accuracy. And as a contribution of the project, we provided the whole project as an open source Jupyter notebook integrated into AI for EU platform with all the necessary instructions. And also we provided a small code for accessing the energy related data from the Helsinki public buildings through the NUCA API. And also we provided a big data set of energy related data as an asset. So we have provided 3 different data sets, daily data set including weather and electricity related data, as well as hourly data with the same purpose. And also we provided another big data set about energy consumption of with daily periodicity, containing about 600,000 building level electricity consumption observations from more than 1,000 buildings located in Helsinki. So this was the main project results, and thank you for your attention and questions if you have.
Any questions for Jakob? Thank you very much, Jakob, for all the great work.
Thank you.
Have any questions from the audience? I don't see any, but I would like to ask you, how do you see yourselves moving forward from now on? Do you have some ideas for the future on how you can improve the model, or some other commercial ideas that you can move forward as a company?
So our future steps would be also already the integration of this prototype into our energy monitoring system called N-Control. So the next step would be already to integrate this experimentally proved module into our already existing product and commercialize it.
Thank you very much. Looking forward.
Thank you.
Okay. Thank you very much, Jakob. Let's move to the next presentation, AI for Hotel. Hi, David.
Hi, can you hear me?
Yes.
Okay. So let's share the screen. Let me know if you can see it.
Yeah, we can see it.
Okay. So yeah. So hello, everyone. My name is David Cañadillas. I'm CTO of I-NERGY. I didn't know if I had to present the company, but I have a few slides for that. So we are a company based in Canary Islands, Tenerife, Spain. And we are a spin-off company of the University of La Laguna, meaning that we have some ties with it. And we do a lot of activities, but our core activities are the energy communities development and the forecasting and AI solutions. And this is our team. So let's go to what matters here. So we are going to present this AI for Hotels project, which the idea original was to put into use all this big data that the hotels are storing in their databases, and they are really rarely using. So the background is like hotels are like energy consumers. This is especially true in places where the tourism is our main activity, such as the Canary Islands. And also, in general, hotels are well-managed buildings with sensors and all the equipment already in place. But as I said, this data is rarely put or reach its full potential value. And also, hotels have certain particularities, like the client satisfaction is above everything else. So it's kind of difficult to implement some strategies of energy efficiency sometimes. So our objectives with this project was, on the one side, to reduce the energy consumption and greenhouse gases emissions associated with the hotels, and on the other side, to exploit the full potential of this big data being stored in the database. So to do this, we propose this two-fold solution. Well, on the one side, we forecast the different variables we want to use, like for instance, the occupancy, the energy consumption, the water consumption, etc. And on the other hand, we want to use these forecasts to optimize the processes, the energy processes in the hotel. So like through unit commitment, the best times, and all these kind of strategies. So this is an example of an hotel design with all the different appliances, like the climatization, hot sanitary water, etc. And they kind of have these sensors, and they are storing this data in their databases. And this will be the scheme with our solutions, which will be performing this forecasting with deep learning models. And with these forecasts, we will be able or should be able to optimize different configuration of the hotels, helping them to achieve this energy savings. So during the development of this project, we encountered one important problem, which was the delay on the installation of the sensors and actuators. And this was due to the legal departments of both the hotel and our partner in Madrid, which is the one supplying the sensors, the devices. But yeah, this probably was the worst scenario because we couldn't work on the optimization model. But well, other than that, we work with the forecasting model, so we are kind of happy with that. So our final contribution to the A4U platform was the deep learning models. We provided them like a model, like in a GitHub repository. Also, the data set is fully available to all. And the web app used to interact with the models, we present a demo version, and the full version will require credentials to access it, so not everyone can see it. But with the demo version, you can get a sense of what we are doing there. So yeah, this is the links to these assets. And for the web application, our idea is that the hotel owners and managers will have all the information at a glance in one place. So this is what we want to have for them. And during the development of the project, we realized that they had other needs that we haven't seen in the first place. So with their feedback, we were able to include other tools in the web application that for them are more useful than that we initially thought. So yeah, those are the links to the web application in case you want to check it. And also I put here some screenshots for you to feel how they are. So first you can define where your hotel is, take a lot of information like where are your clients coming from, the start, the number of rooms, the maximum capacity, etc. Then you also have like individual views for each of the hotels you manage, like with the daily forecasts for occupancy, energy, weather, electricity price, etc. And also the clients or the users if they want to analyze the data that they have input or we have captured from the APIs, they can do it in this data analysis view. And this is an example of one of the things that I said, that the hotel owners have these needs to analyze different tariff offers, and we provide them with a tool to do so by simulating the last year electricity consumption with the offer that they have received. So they input here the different offers, and they can analyze which one is better for them. So the final IT architecture, so right now everything is built on AWS, but if the product scales up, we will be looking for different ways to implement all. And regarding the KPIs, we have complete more than half that the ones we propose. We couldn't evaluate 3 of them because we couldn't develop the optimization models due to the delays I mentioned earlier. And the one we failed was the one with of the installations, because we weren't able to do it. No. So I think the most important here is that all our models have like less than a 6% of normalized root mean square error on average. So this is very, very valuable, I would say. And I would say I will go quickly here. So moving forward, our idea is to work with other hotels, which we are already doing. We are working with 4 hotels at the moment. They are giving us their data, and we are using their data to expand our models to improve their performance. And once we have everything in place, we will evaluate if that's what they want, and we will see the real commercial value of the tool. This is our business model canvas, which can be slightly modified with these other things that I mentioned, like the tools they want to have and they don't have. But in general, we will provide the service the software as a service, and they will, or the revenue streams will be like, they will pay like some monthly fee to use the tool. Also, with the first hotels, our clients, we are doing it, we are taking it like slow, so we are not receiving that much fund from that part, and we are only gaining money for the savings we will provide to them. So some lessons learned here, at least in the hotel sector, we have identified that they have very little knowledge about the energy flows in their hotel. So, and they have asked us to be their energy assessor. So we have identified that there is a role here that they want to have and they don't have. And also we have see that the feedback from the clients and talking regularly with them is essential to provide them the solutions they want. So what we want to do with our tools is to compress all these things and provide a package for each hotel manager that wants to manage their energy, in a smart way. So for our product, we have this kind of roadmap. When now we are working with more data, we will be able to retrain the models and improve the performance. The web app is still under development, and we will include more features in the future. The optimization routines, we still don't have any results, but they will be highly customized because the different cases that the hotels have different possibilities, so they have to be tailored. And the idea is to have all the information for them in one site, so they can have a quick view at a glance of of what's happening in their hotels once the devices are installed. And we propose like a roadmap for hotel owners, which, as I said, we are working with 4 of them, and until the modeling phase, all's free. So we are seeing how this works and see if we can continue with this plan in the future. But all will end with this access to the web app where they will have all the information in one place. And yeah, as well as the things that we have discussed, we kind of propose them to have other services. Some of them are already being contracted, and others we will see in the future once we evaluate if the tool has this commercial value, which we think it does. So that's all. I want to thank I-NERGY for the opportunity, and yeah, we hope that we can continue or at least finish that part of the optimization with the second call. I don't know if it will be possible, but at least we will try to do it. And yeah, thank you everyone. And if you have any questions.
Thank you very much, David. Any questions from the audience? No. So thank you very much, David, for making the best out of the situation, given the difficulties you had. But this is real life. You know, a lot of things, especially when it comes to legal. I think they usually are a main obstacle for innovation. So this is something that everybody needs to take into consideration. So thank you for trying to make it again the best out of the situation. Just a quick question from me. How roughly are do you estimate the savings out doing such analysis for the hotels, roughly, let's speaking? And because I guess this is also one of your winning points when you talk with the hotel owners, right?
Yeah, so the savings in energy by themselves, like optimization, we cannot evaluate them because we don't have the data. But one thing that I mentioned in the document, not in the presentation, but with this tariff offer analysis, they can save like tens of thousands of euros, and with zero investment from their part. So this is a tool that for them is like, okay, I need someone to analyze these offers and tell me which one to select. And they really see a immediate impact. So right now, as I said, we are in continuous talk with them, and of course, in the future, I would like to estimate, to have a number to say, okay, we are able with our optimization models to save up to 10%, which was what we said in the KPIs, and I think it's achievable. But right now, anything I would tell you, it will be like a magic. So I can't tell.
Okay, thank you very much for your great presentation and for contribution. So let's move on to the next presentation now.
Okay. Thank you.
I don't see any other questions. So the next presentation for AI for hydro.
Yes, hi everybody.
Hi, Gunther.
Just share my screen. All right, so thanks for having me today. My name is Gunther. I'm the co-founder and CEO of Lexatexa. We are a spin-off from Humboldt University in Berlin. Thanks, Thomas. Thanks, Spiros, for your support during the program. And let me run you through through our development. So we are active in, or Lexatexa is active in enterprise AI. That's a rather broad concept for speeding up the development of AI and data-driven solutions, particularly in the energy sector. And in this program, in this project, we focus on extending the remaining useful life of pellet turbines. But let me give you a brief overview of and some context about the hydro power sector. So hydro power plants are actually they're pretty important and pretty essential in stabilizing the grid, particularly now that we're having more stochastic energy sources feeding into the system. That is solar coming in or wind is coming in, and the grid needs to be stabilized. And hydro is nearly perfect for this because it's clean. It doesn't have emissions. And it also can generate base load capable energy within split seconds. So it's really important to stabilize the grid and to jump in if other sources cannot provide energy. However, particularly what we see in hydro is they're facing two essential problems. And one of the problems is that it's not enough to have to come with like an academic point of view and to provide a data-driven solution that is like a mathematical model or something like this. Really, what the industry needs is a way to integrate these results into their legacy processes and their legacy IT. So if we just come along and we have great results from analyzing data, that's really not going to help them much because they won't be able to integrate it. So that's one aspect, and I will be coming back to this in a minute. And there is a second aspect, second part of the problem that we need to keep on the agenda. That is particularly in hydro, we have the situation that we have a lot of old equipment, and old means the typical hydropower plant that we see today is about 30, sometimes 40 years old. And here's a chart that gives you an idea. The blue bars signal the number of hydropower generators that were built, and you see that most of them were built in the 80s. And this is data just for Canada, but it looks a lot alike in Europe and also in Asia. So the power generating facilities that we see today, they tend to be old, and it's legacy aged infrastructure, and we have little to no data about this historic data about this infrastructure. So what we provide is basically a software framework that helps hydropower companies to build, to validate, to test, and to integrate and to scale data-driven solutions rapidly. Let me run you through our project again, which was focused on the extending the remaining useful life for a specific type of turbines, which is called Pelton turbines. You see one of these Pelton turbines here in the image. So you have different types of turbines. Pelton turbines, they have this bucket, and there are other turbines like Francis turbines. They look more like a blade system, like the ones you know from in airplane engines, for example. Let me give you a high-level overview of the architecture that we are currently implementing and using partially. Coming back to the initial point I made is that it is not enough just to have a mathematical model. You have to be able to integrate that into existing infrastructure, and particularly and also very important in existing processes. So what you see here is a high-level architecture slide, and of modules that we are implementing. On the left-hand side, we start with supplier data integration. That is data that we get from customers, and it's non-trivial to onboard this data because you have myriads of different systems, and you need to make it as painless as possible to onboard the data that's coming from customers. So currently we have a broad range of connectors that is to speed up the process, to connect and hook up the systems in place already, and to onboard data. We also have some very fundamental IoT devices, but we also integrate existing IoT devices to read data. In the project that I will run you through is we use SCADA data. In some use cases, we onboard external data sources. And what's important is that we can cover security and compliance issues. And then once we have the results and the models, we need to be able to integrate them back into the legacy systems, and therefore we use a REST API system. So in a nutshell, this is the architecture that we are implementing. And now let me run you through the project. So the remaining useful life is typically defined, or in the case of Pelton turbines, it is defined as the thickness of the turbine buckets or plates. So consider the following scenario: that you have that turbine that typically lives in a housing, and that housing is you can't just stop the turbine and then walk in and take your measurements and validate that everything is right. So what the operator typically does is like every 2 years, sometimes every 3 years, sometimes even longer, they stop the turbine, and then it's a pretty complex, for security reasons, a pretty complex process to open that turbine housing, and then someone has to climb in, take the measurements manually, and so in between these two measurements, they basically operate the turbine blindly. They don't really know what's the status of that turbine. So what happens in reality is you have what is marked here in red on the x-axis, you see the time, and what is marked in red, you typically have measurements. Like these measurements are 2 years apart or 3 years apart. So you have one measurement here, let's call it T0, and you have another measurement 2 years later, and let's call it T2. In between, you're basically flying blind. So what we had to do in the first step is to work with the engineers of our data partner, which is Salzburg AG. They operate more than 30 hydropower plants in Austria. So we had to the engineers had to define rules, basically how they would think that the operation or the wear of that turbine type would look like. And you can imagine that you have 5 different engineers, and they come up with 7 different ways of how they think the operation would work. So the first step we had to do is to come up with rules, basically a rule-based system that would describe the assumed operation of the system. And then in the second step, what we did is for each of the SCADA parameters, we had access to about 65 different measurements coming from the SCADA system. The measurements are done with a frequency of about 100 measurements per second. So what we had to do is we had to boil these measurements down to much broader intervals. In the end, we ended up with about 15 minutes. So we condensed this data to 15-minute intervals. And what we did for each of the 65 SCADA parameters, we built the functional dependencies, and I'll run you through this in a minute. Let's go step by step here. So if we now zoom out, you see the orange line, that is basically the history, and then you see the blue line and the red lines. That is based on the models and the operational parameters, the operation that the system would assume. So the blue corridor would make the assumption that we keep operating the system the same way it was operated in the past years, and the red corridor is the prediction of the model that is made based on adjusting a couple of parameters that we exposed. So in the end, it's a functional dependency of operational parameters. And here you have to keep in mind that depending on environmental parameters like what kind of water do I use? For example, is it from what type of mountain is it coming? Is it glacier water? Is it rainwater? Are there segments in the water? Is it summer? Is it winter? What's the temperature? So these are all parameters that play an important role in the operation of the turbines, and we expose these parameters so the customer can play with it, and they can basically answer two different questions. That is the first question: if I keep running the turbine the way I did in the past, show me for how long I can keep running that turbine. And the second question they can answer is, how do I have to change the parameters, like the number of stops or for how long I run the turbine, let's say, given the type of water I have, in order to reach a particular point in time, basically to extend the life of that turbine. So, and also what's very important is we, for verification purposes, we have to expose the information of what parameters have what kind of impact on the prediction. That was very important for the engineers to validate if the system found the correct functional dependencies. So this is what you see here. So given time, I skip some of the slides. Perhaps one brief additional information here. Basically, as a side result, we also got information that would enable us to do anomaly detection for the turbine, because what typically happens is that if you look at the green line up here, that looks, if you look at it as from an engineering perspective, it looks perfectly straight and it doesn't look like there is an anomaly. But you see the red flags here. So if we, and that will indicate to the engineers, have a look at this particular scenario here, because there might be anomalies. And here is why, right? Because a typical engineer, they wouldn't see this anomaly because it's exactly in the expected range of values. But given that we build the functional dependencies, the system would give them additional information like, okay, so what you observe here is, it looks like everything is okay, but really it doesn't make sense, because if we observe the additional impacting variables and they have particular values, then it doesn't make sense to observe this target value. And this would direct the root cause finding of the engineers. So that was basically a byproduct of the activities here. Let's skip the video of how to integrate the API. So as a result, we developed predictive models based mostly on XGBoost, tree-based algorithms, to predict the remaining useful life of Pelton hydro turbines. That was based on real-world data coming from about 65 variables read directly from live SCADA systems. We published the models on the AI on demand and AI for experiments platforms, and we exposed the API in two different ways. You can actually access the API if you download the container that we provided, which acts as a proxy, and you can directly talk to the API if you go to our micro websites, AI for Hydro at Lexotexo. So very briefly to the business side, what we provide as a platform provider, we provide solutions along the entire value chain, which is typically sales, production, and maintenance. And you see here some solutions we roll out already, for example, for predictive scheduling of assets. And what is marked here in the red circle is the remaining useful life. And what we plan to do is that at a later stage, all of these different solutions, they will be able to talk to each other. And we provide a complete set of solutions for the energy sector. All right, so given time, I stop here. Thanks for your attention, and looking forward to taking your questions.
Thank you very much, Gunther. Any questions? I guess the audience is a bit shy today. It's not as engaging as in a physical event, so. But anyway, just a quick question for you also. What are your next steps as a company? What some of your visions or strategy for the next years?
Yeah. So basically, it's about two things. So we're rolling out solutions already to some real world customers. So we do have business traction. So number one is we need to extend this business traction. So we now have customers in Austria and Switzerland. We would add additional countries, and also we plan to extend the range of solutions that we provide. So some of these solutions that you see here, we have already. So remain useful life. We just started as a pilot for pellet turbines. We have solutions for Francis already. So what we are working on is extending the range of these solutions.
Thank you very much, Gunther. It was a great presentation and your contribution, and as well as I think it's one of the most interesting use cases. So thank you very much for the presentation.
Thanks much for your support.
So we have one more presentation before the break. Let's go to demand data.
Hi guys, I hope you can all hear me. I'll be sharing my screen shortly. There you go. Okay, last presentation before lunch, so everybody cheer up. I'm Christopher Jackson, one of the co-founders at Advanced Infrastructure, and I will be talking you through the project that we've done relating to smart meter data. First of all, describing the problem. It's well known that access to 15-minute electricity smart meter consumption data could save customers over 600 million euros per year European-wide. There have been a number of studies which have investigated how better access to this data would deliver value to customers. However, the problem is that in most European jurisdictions, access to smart meter data is difficult. This is because it's classified as personal data and therefore is protected under GDPR. There are also many commercial and governance barriers to access to individual building level smart meter data, such as competition considerations. So a lot of the final commercial aim of this project is to find ways to build a smart meter data repository which somehow contains sufficient information for energy modeling applications, but sidesteps the problems of GDPR. And the end goal is to try and release that 600 million euros into the industry to make those savings to customers. So explaining the problem with the aid of a diagram. On the left-hand side, we have what the current industry approach is to satisfy privacy concerns under GDPR. And that is simply to aggregate customers, individual buildings, into groups of at a minimum 5, but often they're aggregated at the connection point to transformers. So in this particular example, you've got 20 buildings, all with different characteristics, and that's visualized by the different colors of these buildings. Some are 2-story and 3-story, some have electric vehicle charge points, and some have electrified heating, some have gas heating. So they all have different customer demand profiles, but they also have different building attributes. And that's what we're representing in the coloring system here. They've also got different occupier attributes. So the individuals that live in these buildings, they're at different ages, they have different sizes of families, some work from home and some work in an office. But all of these are mixed together, and the demographic and building breakup within that sample is lost. And the demand profile is aggregated up to the transformer load level, and that's all that's recorded. So the problem is that the information around the building attributes and the occupier attributes is lost. And the reason why this is done is because the methods by which data privacy is maintained isn't really understood by the industry, and they just tend to aggregate them as the first line of protection to ensure compliance with GDPR. Our approach is on the right-hand side, where we create a classification of these different building attributes and occupier attributes, and we assign buildings, let's say a minimum of 5 of them in each of these in each of these classification sizes. So our goal has essentially been to tune the classification schema so there is at minimum 5 customers in each classification grouping. However, that improves the forecasting ability because you're essentially collating like buildings with similar demand profiles and like occupiers with a similar usage profiles as well. On the next slide, I'm just highlighting the 4-step process that we have. First of all, we take account of the geography and climate in the particular country in question. We've been focusing on the UK. Secondly, we obtain building data, building attribute data for the entire building stock, and we tune the classification. We also do this with social demographic data, so there is fintech data and credit records and credit reference data that we can also use as well. Then we obtain the smart meter data, apply the classification, and then undertake the model fit. Just to explain one of the modifications we had to make, we couldn't get individual household level smart meter data, but we could get it aggregated by region, as I spoke before. However, since we had the individual building attributes and occupier attributes assigned to those buildings, inside that load profile, we were able to run our machine learning work packages and essentially disaggregate that data. I'm now going to change screens and switch to one of my colleagues who will give you a talk through of what they did. Can you tell me whether you can hear my colleague, by the way?
No, we cannot hear the sound, unfortunately.
Okay, well, I'll simply narrate what he's doing. He's essentially talking through one of the Jupyter notebooks that we used for the machine learning approaches. And I will skip ahead to the principal component analysis that we did. Now, we had about 200 features in the machine learning model, but as you can see, the top 5 contain most of the explainability, and these were attributes such as occupier age and building size. There was a very long tail of other attributes which had a reduced explainability of the demand profiles. And this is an example of actual versus predicted. And I just want to find where we actually had our error rating, which was, from memory, about 87 or 84. There, a root mean squared of 0.89, which was, according to our technical KPI, was 85%. So that led to a successful forecasting tool. Returning to the presentation. So the outputs for the AI on-demand platform are available for you to view, including some of the data sets and the notebooks and models, and the hyperlink is shown in the presentation here. In terms of the business model, these profiles, these building level smart meter profiles are really important for long-term strategic planning in the energy transition. 4 of our customer segments are shown here. These include, from the right-hand side, the consultants who essentially design and deploy many low-carbon technologies, such as Beringer, Arup, and WSP. Also, second from the right, whole systems optimization tools. Some of these originate from European collaborations such as Calliope. These profiles will improve the accuracy of the building level modeling. And there are other routes to market through GIS tool providers, including ERIS and ArcGIS, and also single technology modeling tools can benefit from granular building level energy demand profiles. And we'll be progressively taking this product to market in 2023, and have already some trials underway with these vendors. Thank you, and any questions?
Okay, any questions? Thank you very much, Christopher. Do you have any questions? I would like to ask you, what do you think about some ethical or data privacy considerations that you had during the project, and how this can be solved in the future? What recommendation you would have, for instance, to organizations that currently working on ethics and data privacy solutions, especially when you need to have data that will optimize a lot the energy consumption, so they have a big impact, but on the other hand, you need to protect the data, the privacy of this data.
So I would really encourage a European study to look at how different regulatory, how countries have had different regulatory decisions, because we came across Spain and Sweden, who had more relaxed approaches to the classification of energy demand as personal data. We also came across contradictions within the UK between the 6 electricity operators. They all had different interpretations of privacy, but none of them had a way to quantify the risk of re-identification. So I'd say 2 things. Let's look at the contradictions within jurisdictions and between countries, and have an honest conversation as to why some countries are more relaxed than others. But also, I think there needs to be developed quantitative tools to interpret the qualitative regulation. And a big problem we've found is the risk of re-identification. There's no sophisticated way of measuring this. So when you try and explain to a lawyer the statistical likelihood of a re-identification, they don't really want to put their job on the line to try and understand it. So we need to translate the qualitative into the quantitative and vice versa.
Thank you very much, Christopher, and thank you for the great work that you have done, and all the contribution.
Thank you.
So we are just in time for a break, and we will return in 10 minutes. It's a small break, but necessary. So thank you.
Okay, thank you. Thanks.
Hi all. I hope everyone is back. And we can continue with the next presentation, E-Model Ops.
Yes, great, absolutely. So hello everyone, I'm Sebastian, co-founder and CEO at Rebase Energy, and we have been working on the E-Model Ops project in the I-NERGY. So yeah, I hope that you can all now see my screen, and I will set the timer to get started. So yes, so Rebase Energy, what are we all about? So we're an energy modeling platform to optimize, simulate and forecast distributed energy systems. And in the I-NERGY project, we're really focused on the forecasting part. So that's E-Model Ops for forecasting. So why forecasting? Well, the energy system is transitioning from a centralized and stable system to a much more weather-dependent one. And this is a huge challenge because of the intermittency and volatility that comes with that. So in order to balance, operate, and trade the energy system of tomorrow, we need accurate energy forecasting. And this is everything from solar, wind, weather forecast, and price forecasts. So this all goes into several different applications, such as, for instance, grid operations and energy trading, but also more local operations, such as operating buildings, building energy management systems, and even home energy management systems. And of course, it's all the usual benefits that we can get from forecasting, such as reducing the cost, saving energy and cost, reducing the risk, and increasing our profits in markets. So just for everyone to understand a little bit what goes into a forecasting pipeline. So essentially, since the energy system is so dependent on the weather, the forecasting pipeline starts actually fairly long bit back. So with collecting of data from weather sensors or satellites into these numerical weather prediction models that creates numerical calculations about what the weather is going to be like tomorrow or the day after tomorrow. And then we also have, the machine learning part of it. How can we then tune these models in order, or this data that comes from these models rather, in order to make them as useful and valuable as possible for the energy system? And in the end, we do need to take decisions based on this data, and that's up to the operators, the energy traders, and so on. And what we have been working on at Rebase for a fair amount of time is creating flexible APIs to extract this data from these weather models, for instance, and other satellite data. And what was really, we were really curious and excited to work about in this project was really on the modeling side, actually extracting value from this data and making it as useful as possible for energy forecasting applications. So that's what we've been focusing on here. And then, of course, we need integrations with APIs and so on for downstream operations, but that has not been the focus of this project. So, all right. So the I-NERGY project had several phases and two main milestones. So it was mainly about developing the E-Model Ops platform and making it scalable from the beginning and easy to use for data scientists and engineers. And secondly, it was about experimentation, deploying the dashboards, deploying the assets for the AI on demand platform. So the architecture that we've been working on looks like this. So what you see here is two of the key user personas that we envision with this tool, which is the data scientist up here and energy engineer down here. So essentially, the tool that we're creating enables the data scientists to create a project, integrate their GitHub, their Colab, and the Streamlit workflows to create pipelines that are reproducible and maintainable in a state-of-the-art tool called Airflow for creating pipelines. Then to scale these pipelines up, for example, for experiment tracking or hyperparameter testing on a Kubernetes cluster, save all the data, and then deploy, when you have a model that you're happy with, deploy these pipelines back into, for instance, Streamlit apps that can be used by non-coders, energy engineers or operators or data consumers. So that's the whole idea with this workflow. So it's kind of a dual workflow, two user personas that we envision to use this tooling then. And here's a small video showing how it works. So essentially, you can create a project, much like you do in GitHub or any other collaboration platform, really. When the project is created, you then get a Colab notebook with some boilerplate code in it that helps you get started quickly. So essentially, it enables you to create a forecasting pipeline in this case, to train and predict. And we create this pipeline in a way that it's, as I mentioned, reproducible and maintainable over time. So we then upload a target data set in the pipeline, and as you can see here, so in this case, it's a wind forecast data set. We take in the feature data, which comes from weather forecasting models, such as, for instance, the German open dataset Deutsche Wetterdienst model. That's a numerical weather prediction model. And we can then create these pipelines that we then deploy and run on an inference infrastructure. And in the end, you can then query these models that you have created to get new prediction results on feature data that the model has not seen yet, so input data that the model has not seen. And lastly, of course, deploying the model and making it easy for the data scientists to get that into the cloud and make an API out of that. Here, going back to the platform, you can then see the model that are deployed and host them as an API and as an app. In this case, we're using Streamlit as the main framework to creating these apps, which you can see here. So we created a small template inference app where you can then choose the time of the forecast that you want, and then it will display that in the user interface, and you're also able to download that data as a CSV or Excel file. Okay, speeding up here a little bit to be aware of time. So we also had a real test case that we evaluated these forecasting algorithms on. And we were really curious or happy to find this open data set during actually the project that made us shift a little bit focus from the demand to supply forecasting. So this is a data set that comes from the Norwegian Water Resource and Energy Directorate. And it's an hourly data set of wind plant level data from 51 different wind farms in Norway. And we've used the splits here that you can see to train and validate models on this data for energy forecasting for these wind farms. And this is some of the vocabulary that we will see in the slides very soon. So essentially looking into the different types of models that we created with physical models, but also with machine learning models. Okay, and our main conclusion was that actually using machine learning has a big value, so we can reduce the error in the forecast models by more than 50% by applying some simple machine learning models and reanalysis data. But what was even more interesting, we think, in this project was that the use of historical forecast data and then further the use of ensemble data, so all these models that have a prefix of ENS are using ensemble weather data from several different models, increased the performance significantly. So reduced the error rate of more than 26%. And the error rate that we've been using here, or the error metric that we've been using, is the normalized mean absolute error based on wind power capacity. So a little bit about the contributions that we made to the AI on demand platform. So there's a couple of videos on that. So first is the data set that we thought was quite unique, and we really wanted to contribute that to the platform in order to enable other data scientists, startups, and researchers to work with this data in a more streamlined way and find new algorithms that could be applied for this data. So essentially, it enables the researcher to spin up their own Kubernetes cluster that they can use to deploy our service that has been hosted in dataset that's been hosted in the AI on Demand platform. Then to do a port forward to the UI in order to explore this dataset. And we made a small example UI here, which essentially enables you to choose the type of data that you would like to extract. And we connected this with our dataset that we have available openly on our website as well. So this is then the Norwegian wind power forecasting dataset. We input that, and we also input the asset of the wind farm that we want to access, and we then get a visualization of the data, so you can play around with it in this app. So I will now fast forward a little bit to be conscious of time again. So essentially, yeah, you can download the data as well through the Excel and CSV files. The second contribution that we did was on the model side. So here we actually create an energy forecasting model that is forecasting wind power. So let me scroll forward here a little bit. So the user interface now looks slightly different. Sorry, maybe I got that wrong. So let's see here if I can. Yeah, here we go. So the model prediction user interface enables you then to upload a train and test data set that you have locally with the features and the target values. And then to upload a completely new feature set, data set that you don't have target for in order to create predictions with the assets that's deployed on the AI on Demand platform. And here you can see a prediction, example prediction that comes out from this model. Right. So summing this up, we have developed a scalable platform to create and iterate and reproduce energy models for forecasting. We delivered on all APIs but one, and that's essentially related to more user interface features such as interoperability or interpretability rather, and some error matrices. But we decided to really focus on the contribution to the AI on Demand platform instead of those front-end features. We have achieved state-of-the-art accuracy on wind power, which is around 9%. So we were already at 7.5% mean absolute error. But that was not aligned with the KPI that we set up in the beginning. That was 3%, but that was relating to demand forecasting. So we actually did a test with the same model on demand forecasting as well, and we saw that we could achieve that KPI if we used a demand forecasting dataset instead. Obviously, wind power is more difficult to predict than energy demand. So we deployed 3 assets on the AI on Demand platform, including this dataset, the model, and the data broker. And we're now in discussion with 18 closed beta testers to try out our solution and hopefully bring it to market by next year. Thank you so much. So really happy to connect with everyone here. So feel free to follow us on LinkedIn or join our Slack. Would be really keen to work together and talk together about energy modeling.
Thank you very much, Sebastian. Any questions from the audience? So yes, Sotiris, go ahead.
Yes, hi, this is Sotiris Pelekis. Great job, and it was a pleasure to work with you within the project. As far as we understand, basically I have a question on the forecast, because it's obvious that you use forecasts from many sources and you combine them and you can compare amongst the performance that each one offers. Do you have, let's say, is there a page of your company where you mention from what kind of sources and what kind of models, or for example the physical or the simulated ones? Is there a documentation or something where you mention from where you collect all the stuff?
Yes, there is documentation.
Okay.
There is documentation on that. I didn't include in this presentation, but I can definitely send it to anyone that's interested. So yeah, ping me on email or join our Slack, and I can share it there as well. But there is documentation on where we get the data sources from. Those come mainly from, weather institutes that publish their data open source, and that's where we get the data in from. So then we have created essentially an API on top of that to enable data scientists to work more in a more cleaner manner or streamlined manner with this data. Yeah. And by the way, thanks a lot, Satiris, for all the valuable feedback during the project. It was it was great.
Thank you.
Thank you, Sotiris. Thank you, Sebastian. Any other questions? No. Thank you again for your great contribution. Wish you the best in the next steps.
Yeah. Thank you for the support, and bye-bye.
It was a pleasure. Next, maintenance.
Thank you very much for the attention. I will share my screen and just tell me if you can see it. Okay, do you confirm you can see the presentation?
Yes.
Very good. Okay, full time. Okay, good afternoon, everyone, and thanks for joining us. I am Veronica Brizzi, and I am Industrial AI Advisor in MIPU, Energy Data. Today with me there are also Stefania Oliviero, Project Leader and Product Owner of the AI Solution, and Renato Marchetti, Industrial Data Scientist. MIPU is born with the scope of bringing predictions into factories and cities, with a strong willing of democratizing AI. With this focus, we present today MineTnet, a plug-and-play AI solution for anomaly detection in LVMV transformers. Let's start with some context. In Europe, we count around 10 million kilometers of power lines, and 99% of network customers are connected to the grid. About steam brings us to a 4 million transformer installed in Europe. Since 99% of customers are connected to the grid, almost all the power distributed through electric lines passes through LVMV transformers. It counts around 2,300 terawatt-hours a year. Usually, a transformer loses 2 to 6% power in the sold transformation due to anomalies or inefficiencies. Doing the math, this counts at least 40 terawatt-hour lost only in the transformation each year. Power is usually lost as heat, and that's why most of the transformers are already equipped with a basic temperature sensor. This means that these sensors are already available for use. MineTnet solution aims at identifying in advance those losses, monitoring those already available temperatures with a suite of AI models, enabling a much more precise monitoring with respect to the static threshold. Based on those 4 temperatures and the hour of the day, MineTnet defines the behavior of a transformer and evaluates anomalies on the analyzed period. Depending on the needs, the anomaly detection can be done in an exploratory way or in a real-time monitoring. MineTnet solution is structured with 4 parallel artificial intelligence models evaluating each temperature with respect to all the others and with respect to the reference behavior, and an expert system evaluating the shift between real and predicted temperature in order to identify anomalies. Thanks to MineTnet, it will be possible to contribute to sustainable innovation and low-carbon economy in the energy sector. The expected outcomes in a scenario in which all the transformers will be equipped with MineTnet real-time monitoring is an increased lifespan of assets, a 3 to 4% energy savings thanks to reduced power losses, and less wastes thanks to a more efficient transformation. From the technical point of view, the model will be able to detect 80% of anomalies with a temperature prediction as precise as 90 to 97% depending on the method, as defined in the technical KPI. MineTnet is available on the AIoT platform together with a synthetic dataset containing the 4 temperatures, 1 of the core and 3 from the windings, and the hour. The synthetic dataset is created starting from specific operating conditions and using the AI model suite. MineTnet can be used both using a simple web app designed for not IT user or by downloading and installing the Docker. The second usage is designed for including MineTnet use into existing monitoring system. Both ways call MyInternet AI core, which provides 3 different calls for 2 different methods. The first method provides the data to be tested to MyInternet, which does a retraining of the model based on new data and identifies anomalies based on the difference between prediction and real data. The mathematical hypothesis validated during the funding project for this method is that the AI suite can be updated based on different datasets in order to widen the representativity of the models with respect to different transformers. The precision of this approach is slightly lower, but still within the KPI of 90% set as a threshold. The second method, implemented with the scope of providing a more scalable and precise solution, enables the user to create a unique model related to the specific asset. With this unique model, the user or an external system provides the new data to be tested together with the unique ID of the model, and the systems calls the unique model associated with the reference ID and provides a prediction based on the new data. We guarantee a data volume up to 200 megabytes, higher than the minimal technical KPI of 0.5 megabyte. MyInternet solution has been studied to be as easy and solid as possible, optimized for industrial uses thanks to engineering approach, with only 4 sensors to be used and maintain the 4 temperatures. Since it provides 2 different methods for exploration or real-time monitoring, it is quite flexible and aligned to different users' needs. One of the methods enables the user to create a unique ID model so that the precision of anomaly detection can be maximized. From the architectural point of view, MyInternet uses an API gateway and a middleware calling MyInternet methods. The middleware is built in a Docker container, and you can download it from an open source Git repository, which is available on the IoT platform. Now we will share with you some basic models, some basic example of how the solution can be used. You see that on the AI on demand platform, you will find both the open dataset and this open source technology, both the web app and the Docker solution. Let's see first the web application, which is the application studied for people who are not ITs, so do not have an IT expertise. We have said that there are 3 calls for 2 different methods. Now we see the third method, which is the explore anomalies method. In this method, you can upload your CSV because the web application runs on CSVs while the Docker runs on JSON, and we will see both of them. We have now uploaded the dataset. It is exploring, and we see the result in the second part of the web application in the output dataset. And the output of the web application is this output dataset and the alert plot. Both are available and can be downloaded if needed. Inside the output dataset, you see that from the 4 columns we have used, you can have all the prediction for each of the 4 temperatures. And here we can see the prediction and the anomalies which have been explored. In this test here, we do not expect so many anomalies because it was a good behavior dataset. The second call, which enables the second method, is create my model. So here you need to upload, again, a CSV file with the reference behavior of a specific transformer. So you have your transformer, your 4 temperature, you upload the data. You see here the user has uploaded the data, and you have the data preview. Now it is running, and once it has been training, you have to save the unique ID model, and this unique ID is a very strict representation of your transformer, so it can be used for doing real-time monitoring and other predictions on different datasets. Let's see now how to do the prediction using the model. So this is, again, the second method in which I have to do monitoring. I need 2 things. First, the new data, and second, my personal code, my unique ID code. Here I have uploaded I am uploading my CSV. I have uploaded it. And again, we see that the model creates an output dataset and creates also an evaluation of alerts. In this case, in this scenario, we actually had a problem in the second part of the analysis. We can see here the anomalies are those red triangles, so you can see that the model actually identified the alarms. You can also navigate all the information, but of course, the visualization is easier to be used. This is the web application, so the part thought and designed for non-IT users. So, for example, maintenance responsible or energy managers who wants to do some analysis or do real-time monitoring, for example, once a month in the web application. If instead you want to use maintenance inside a real-time monitoring system, for example, a BMS or an energy management system or whatsoever system for monitoring MBI, you can use directly the Docker. This is the video for mounting the Docker and using the Docker. Again, we will see the 3 different calls for the 2 methods, so the exploring, the training, so the creation of the model, and the prediction. This first is train and predict, so the exploration of the dataset. You see here that we have the structure of the API call and the structure of the JSON call. In the first, for non-IT, you just use CSVs, and it's quite simple. Here instead, you need to use JSON file, and it is thought to be as standardized as possible for a machine-to-machine interface, so machine-to-machine call. You see here that there are, in the meanwhile, while I was talking, the first prediction has been done. So the first exploration has been done on the JSON file. It has been selected. Let's see now the second call. So the train, the create my ID model. Here you see that there is a different method call for the different specific action we want to apply. Again, you need to provide the JSON, you need to provide the sending. While it is sending, it is calculating again the model in order for you to have a unique ID to use for the next time predictions. It will take a while to do the training, of course, depending on how big the training set is. And now we have the model code, which is the one we previously saw on the web application as an output string in the web application, of course. Third call, prediction. Again, you need to give the JSON file so that the new data set you want to do prediction on, and the model ID. So you see that there is here the code model ID we have created in the first call. This is very, very fast because it is just the prediction. And you see here that we have all the predictions, the alert, and the information you need to do anomaly detection on the transformers. Okay. Of course, this is the funding part. The business model we have imagined is structured as follows. In this first funded phase, we are testing the solution, and here you can see some call for actions disseminated in the last month, asking customers to download and use the app to give us a feedback in order to do a fine-tuning on the alarm system, so on the expert system generating the alarms. Once tested in the open source phase of the funded project, maintenance will be offered according to the AI as a service model, where users are required to pay a setup fee and a recurring fee in order to use the solution. Different pricing are designed, and the pricing packages depends on the method used by the user to do specific prediction. The first method related to one-time model and prediction creation is structured in a pay-per-use pricing. So the user will pay a setup fee for the Docker container download and a fixed fee each time the anomaly detection analysis is done. So first method. The second method instead is related to long-term real-time monitoring and is structured as a recurrent fee pricing. The user will pay a setup fee for the Docker container download, a fixed fee each time a new unique model ID is created, and it is included in the first setup for the first creation, and then a monthly fee for the use. So this is our contribution to the AIoT platform. We are very happy to have been given the chance to contribute and also to to be able to implement this new model, which can really impact the energy sector and bring and contribute to sustainable innovation. Of course, if you need some more details, feel free to ask any question you may like, or feel free to contact us. And here you see all the links if you want to go and look for the solution on the IOD platform. Thank you very much for your attention. I think I was around on time, so feel free to ask as many questions as possible.
Thank you very much, Veronica, for the great presentation and overall the good contribution that you had in for the project. I would like to ask you also a question. You know, the AI on demand platform is also, we are all contributors to that. I will say that something on the conclusion. So from your perspectives, which would be the features or the activities that you would like to see in the future in AI on demand in order to help your company better in the future? Which are some key elements that you would expect to see in the future?
I think that on the IOD platform, the idea of having an open dataset, an open portfolio of dataset is quite interesting, because for organization who create AI model, artificial intelligence models, or at least works on deep learning or machine learning, the availability of data is quite a point, because data, you know, are an asset to companies, to organizations, and not everyone, not anyone share its data. So it is quite interesting to have this data, and that's why we also wanted to contribute with a synthetic data set starting from an existing transformer. And the other thing is that, well, I really like contamination. So seeing different ways, different approaches to the same problem is quite interesting for everyone, anyone in the sector. So thank you very much for your contribution.
Thank you very much, Veronica. Okay, let's move on to the next presentation, Smart River.
Yes. Good morning, everybody. I'm sharing the screen. Oh. So I'm Paolo Mazzoli from Ecosystem. I guess you see the screen, and we are an engineering company, and I wish to thank the I-NERGY project for letting us the opportunity of developing Smart River, our digital twin solution for AI-driven forecasting. What is Smart River doing exactly? We are forecasting particularly river discharge, which is the ruler of hydropower energy, and it's a variable of interest for a dam, a river cross-section, and particularly an hydropower plant for energy production. So our idea is that in order to forecast incoming discharge to an hydropower plant, we can put together the local knowledge, which the owner of the plant, the people who owns the Golden Station network has, for example, the time series of discharge, or data from the meteorological ground stations. And then we can put together this information with what comes from the big upstream world, the satellite and other observation world, the upstream forecast services, which is a growing world, for example, from Copernicus. Think about the climate data store of Copernicus from ESA, DataQ from ECNWF, also open forecast data, and put together all this local and big scale information through AI and machine learning. So we had to, in order to do so, we had to think about which could be the best forecast algorithms to use. We had to test alternatives, and thanks also to the project, we had the chance to discuss with the mentors on that. And we have to code in order, mainly through Python, in order to do so. We also tested the world of auto machine learning in order to test many algorithms, forecast algorithms, and get the desired result. Desired result, that is the forecast for the next week or the next month of the incoming discharge. We could have done this also in other ways, for example, through mechanistic change of models, rainfall runoff, but we decided not to go this way and instead to go through machine learning, because we wanted to avoid the complexity that comes with using complex model with many data and many specialistic skills required, in favor of a much more lightweight approach through a few set of data and machine learning algorithms in between, in order to create this very lightweight digital twin of the catchment, and produce the desired result, which is the forecast of discharge and then of energy, using as few data as we can. So we did this way, particularly because we wanted to squeeze information and value out of the growing world of upstream services, in premise Copernicus data store. And because these services are as a global coverage, so if we have to upscale our approach and we want to apply to an hydropower plant which is somewhere in the world, we can do that because we are using data that are available globally. Last but not least, we want to keep the final result and give this in the hands of the user and make it as easy as possible. So that's why also we went for the AI instead of complex model, particularly because this avoids the need of complex and specialized skills, for example, those in hydrologic modeling. Again, we are, as I say, coupling together the upstream satellite and weather forecast information with the local data, and particularly the discharge data from the gauging station, which could be owned by the plant owner itself. We have to assess this information either through API for the public services like Copernicus Data Store, or through FTP access for private repositories to the data owned by the user. Then we have to store all this information in a database, process this time series of information in order to turn them into a database which is suitable for training and machine learning algorithms. We are doing everything this inside the cloud environment, including the final provision of the service, a web service, to the user. So the user is not seeing everything in the background, it's just seeing a one-page service. You can access through a web browser in order to get all the information on the features we have used for training, or the forecasted discharge and energy, and also everything that is related to the accuracy and the error of the forecast we are producing. So through the AID platform, among the many available assets we have uploaded, there's also the prototype of web service you can access. The user logs in by means of simple credentials, and then he gets immediately the plot of all the variables, particularly the incoming discharge and all those features which comes both from the local station and the upstream forecast services I was mentioning that feed the forecasts. You can zoom in the period, in a particular period of interest, and particularly you can zoom in the forecast period. Then beside the feature that feed the forecast, it is provided for the lead times the service has been activated for, the forecast information, both on discharge. You can also see the lumped error metrics and inspect error graphs in order to get a taste on the performances and the error of the forecast we produce. You can also decide to, if it's available, if he has a benchmark, for example, we have typically a trivial benchmark, which is the climatic average of the discharge coming to the plant. He can also decide, if he has this benchmark, to plot the benchmark versus the prediction, like in this case, in the 1 month forecast, we added the available benchmark. Finally, once we have the very plant specific coefficient to turn discharge into energy, we can get also the forecast of the energy production together with the forecast of the incoming discharge. So beside this, which is a demonstration through a simple web page of what we mean by making something very easy and accessible to the final user, we also uploaded all the required assets on the platform, including, as I say, the demonstration web service, the Docker container with the service running, and some core components of the background development, particularly the forecast systems, in form of Jupyter notebooks for Colab, and through a GitHub repository with all the README and the an instruction in order to reuse this part of the asset, which is we think the core part of the asset, the one that runs all the forecast and the machine learning algorithms, and eventually enables to test with not only the test data set we have uploaded, but also with the general data set. Finally, I wanted to give you a glimpse about the market part of the story. That's why we have made all this effort in order to derive and deploy this solution, because there's potentially a huge market made by both reservoir plants, which can make use of the forecast system in order to manage the plant, but also about thousands of small hydropower plants, which is something that we went deeper in during the development, talking with users. And so there's a potentially very huge market that could benefit from optimizing both management and production, and eventually selling to the market by AI-driven forecast service. This led also to a revised pricing strategy. We decided to add a success fee in between. This has all to do, despite all the technical stuff that we can develop and all the errors and the metrics we can show, this has all to do with creating a trustworthy AI solution, because setting up from the very beginning expectation, for example, a minimum level of performance in terms of error of the forecast, and sharing also a part of the risk with the client helps talking to the user. This is our finding during the development, helps creating a trustworthy solution which the user and the producer both can rely on without, let's say, I would say overselling, no, and without creating the risk of misusing the solution we have developed. So that's all from my side. I wish you again to thank you for the opportunity of developing this solution inside the I-NERGY project.
Thank you very much, Paolo, for your great presentation and contribution to the project. Do we have any questions from the audience?
I have a question. Yes. Sebastian, Rebase. So thanks a lot for a great presentation, super interesting. So one of the challenges when forecasting hydropower inflow is, of course, that they have like interdependencies between the power plants. Because I mean, if you run an upstream power plant more, then of course more water will get down to the downstream ones. Is this captured in your modeling techniques, and can you expand a little bit on that?
Well, in our application, I forgot to mention, we have developed the demo in a small hydropower plant in the Apennines with local data. This is not the case of interdependencies that you were mentioning. So we didn't have to face this issue. It was a natural stream flow. That's a much more easier case. But again, it's as long as I would say the human action makes a modification of the time series of flow, like you were mentioning, you need either to be lucky that the AI model captures in the training phase this implicitly captures this in the training phase, or be able to explicitly pass this modification into the time series before training the model. We didn't have the chance to test because this was not the case, but should it be me taking care of this, I would try both the ways. So training, hoping that they didn't change the rules of the plants in the recent years, or trying to get explicitly the rules of release, for example, from the upstream plant, and then manually modify the time series before training. That I would do this way personally.
Thanks.
You're welcome. Thanks a lot.
Any other questions? No. Okay, thank you very much, Paolo.
Thank you.
Moving on to the next presentation, snow power.
Good morning. Can you see my screen?
Yes.
Okay. Well, the last 12 months was the driest year since a century. And this is not only demonstrated by the scientific data that we have, but also by the news and the images that I show here. So in Italy, really in the Po Valley, the water stream in the Po was so small that we see several things emerging from the river. But also in Germany, in our lakes, and in France, this drought was so terrible that really this year it has a terrible impact in terms of water availability for agriculture, for drinking water, for river runoff, and also for power production. Power production not only for hydropower, that is the main topic of my talk, but also for the thermal power plants, because for producing energy from a thermal power plants, you need to cool down the power plants. And with so few water, in Italy we had a lot of problem also in producing, and we were obliged to switch off some thermal power plants. And so I can move okay. I'm Marcello Petitta. I'm one of the founders of Amigo, and I'm here to present Snow Power. That is an AI solution for forecasting hydro energy power in the alpine space. Well, let's start. We already see some other solutions that focus on weather forecast try to forecast the energy available and the energy needs by the population or by the industrial production. And we know very well that we can use weather forecasts for the next 10 days. They are very, very accurate. But what happens when we want to say something that goes beyond the 10 days? Well, we could use different solutions. For example, go back to the coffee fortune reading, or use some new scientific results that are the seasonal forecast and the decadal forecast and subseasonal forecast that are very, very useful, and combine them with several things. So our main goal is to try to predict the hydropower production with 6 months in advance, starting in the winter season. So the first thing that we have to consider is the role of the snow. The snow remain in our mountains and become the main sources for all the rivers, especially around the Alps and the main mountains. The main problem is that when you have snow, you don't need only to see where is the snow, but also the total amount of snow that is present, and so is density. In general, the quantity that is very, very important is the so-called snow water equivalent. So the equivalent quantity of water that you have for a certain quantity of snow. And as you can see from here, snow, depending by the temperature and the amount of water that is coming down, can stratify differently and create different kind of snow. So the first step when you have to produce the rainflow, the runoff, is to understand how many snow is available to be transformed in water. The second part is after the winter season, and when you accumulated all the snow in the mountains, the spring and the summer is arriving, and then the snow is transformed in water that arrive into our river and into our environment. And depending by the environment that you have, at the end, you have a certain amount of water, and this water flow into the river and could be used for energy production using hydropower production. And of course, the second part of our experiment is to transform the amount of available water in form of snow in river flow, in runoff, in order to estimate how much energy you could really produce when you have a dam or a power plant that use the stream flow. For doing that, we created Snow Power. Snow Power is a web interface that allows you to estimate all this information. As you can see, we divided the alpine area in macro basins that are the area which belong to the same water and same water stream. And for all these basins, we have information, of course, geographical information, climatological information, and also information regarding the power plants that we have. When you log in our interface, you can select the different basins, click on it, and for example, you could have something that is related to the monitoring part. So the amount of energy that was generated in the past years, the total runoff, and the snow water equivalent. When you click on time series, you also access to something that could be easily seen. You see these three panels. The first one is the energy produced in gigawatt on kilometer square, the runoff, and the snow water equivalent for different years. All this data have been acquired using open data, and in some specific case, we also had the opportunity to have specific data from power plants. All this data can be downloaded in form of images, of course, but also in forms of data, and can be used in different software for doing the specific analysis that is needed. Okay, and this is everything regarding the past, the monitoring part. But what about the forecasting? Okay, our idea is that we know the amount of water, or snow that arrive in winter. So we know the snow cover. We calculate the snow water equivalent. And starting from February, March, we exploit the great value of seasonal forecast in order to understand how much snow will be transformed in water and then will be available for being transformed in energy. For doing that, we use the seasonal forecast, and we created a sort of risk scale. Because seasonal forecast is not like the normal forecast that tell you exactly what is going to happen, but it's a statistical approach that provides you a sort of a range in which something could happen or not. And we transform this in a risk based on our studies, and I will tell you later how we transform this information in risk. And for each basin, you have a different color scale that goes from green to red and different transparency that tell you the level of risk in the forecasted energy production that we provide to you. And this is very, very important because it could be used by the final users in order to take specific decision on the strategy they want to have for their future. The architecture of our solution is based on Copernicus Global Land Services, based on satellite data, and also Copernicus Climate Change Services. Then we also add other data coming from different databases regarding energy. Everything will be given to a data layer that will do some computation, and then to our process engine. Here, the artificial intelligence part come out, mainly in machine learning using Python and specific artificial intelligence module that we use for evaluate the snow water equivalent, the runoff, and then the energy produced. After that, we arrive to the interactive visualization that I showed you before. In this project, we also provide to all the public some asset. Specifically, we put on the I-NERGY catalog the description and the setup of our machine learning model for the snow water equivalent, a data set of the snow water equivalent for some alpine watersheds. Then we had a Docker containers with the snow water equivalent estimation. And finally, we have a case study in which we really go with all the chain from the snow to the energy produced for a specific case. And this is what is completely available for all the people going to the catalog. Then at the end, snow power, it's a powerful tool for estimate hydroelectric power because it uses seasonal forecasts, but it also uses climate scenarios in order to provide information for how to manage and what will be the future of a specific power station. And finally, we are also able to identify extreme events that are very, very dangerous for the maintenance of the hydropower station. For doing this, we started with a design thinking approach because we interview now, it's about 30 people working in hydropower management from the single worker up to the high level of people that run the company, and we try to understand how our solution could be adapted to their needs. And the design thinking really structured our interview in order to define what is the good nature of our product and how to shape our product in order to fit the needs of our potential customers. And at the end, we created an hypothetical persona that we call Sophia, that is the energy plant manager. And here we describe what are their needs, the gain, the interest that she has, and her pains. And around all this information, based on all this interview we did, we created our product in order to fit the needs of these specific final customers. Yes, because our product has to go to the market in the next few months. We open 9 months to go to the market. And the market opportunity is quite big because we have a total available market that is about 3.3 billion and a specific market that we want to target of 60 million. Of course, all we did could be also used in other markets like infrastructure, agri-food, water, and also insurance. And when we go in the climate service market, we could say that it's still a blue ocean, and Snow Power, actually, compared to other products that are present, is the only one that has all these features that sometimes are not present in the other one. Going back to our business model, we want to sell our product directly to other businesses. So it's a B2B, and specifically energy provider and hydro plants managers. It's a scalable solution, and we expect for the next 3 years about 130 clients with a range of cost for clients that goes from 40,000 euro to 90,000 euro, and to obtain at the end a revenue in 3 years of 700,000 euro. The pricing scheme is like that. We have 3 different approaches: the pay-per-use, the standard package, and the premium package. They have different costs. The first one has 800 euro. You can use once, and you immediately get your data. Then you have your standard package that is linked to 5 users and has some standard feature. And finally, you have the premium package that costs 90,000 euro per year and has also customized features. We have to consider that energy companies spend up to 700,000 euro per year for 1/3 of the feature that we have in Snow Power. So for doing that, we are already in contact with 2 of the largest energy providers in Europe. We are considering to pilot our solution this season, so for the next winter season. Unfortunately, I can't tell the name. The name are written in our report, so it's available to the evaluator. And because we are in a contract agreement and we are developing our contract agreement, and seems that our solution is acquiring some interest from the potential clients. For doing all that, we really need a very good team that is managed by myself. We have our CEO that is another expert in climate. Then Federica Guerrini, that is our artificial intelligence expert with a large experience in predictive model. We have a solution architect, another data scientist, and of course, our front-end developer that really develop everything. We have several contacts and several clients all around the world, and we are happy to be part of the I-NERGY projects because climate is changing, and for next business, we need to adapt to this change. Thank you.
Thank you very much, Marcello. Thanks for the great contribution. Very interesting presentation. Very special market, I would say also. What do you think are some opportunities with machine learning and deep learning that give us more opportunities now, these technologies, compared to the traditional forecast models, and how this would have enabled to also go to such markets?
Yeah, this is very, very important point because there are several things that normal model, the physical models cannot cope with, especially when you have to transform data in information and decision. You really need to use another approach. And especially artificial intelligence could help you to understand what are the decisions that have been taken in the past, even a specific model and a specific data that are available. And mixing the physical approach for describing the snow, the runoff, etc., with the machine learning approach in which you can add the decisions and the effect that all these observation had in the past. It's really something that give you the opportunity to have something, a product that fit exactly the needs of the potential customers.
Thank you. I totally agree. Any other questions from the audience? No. Thank you very much, Marcello, and I wish you the best on your new journey.
Thank you.
Thank you. Let's go to the next presentation, the final presentation for today, superpower.
Hi.
Hi, Carlos.
Let me share the screen. So last but not least, we are the project Superpower, and our goal has been to include super resolution for power line inspection. And I will start with a brief story and objectives of our company, and then I will finish with the idea of Superpower and what have we done. So probably right now you are all sick, tired of listening about drones, because everyone has a drone. The niece has a drone, a friend has a drone, everyone has a drone. This is a commoditized market that there are plenty of companies, and every day are new companies, and it's kind of the Wild West of aerospace. But let me tell you something. Do you know how many power lines are there in Europe? There are over 5 million kilometers of power line that are critical for the electrification of society. And today, in 2022, the main aerial inspection, the main tools to inspect these power lines are on-foot inspections, which are low-cost, low-quality inspection that do not capture digital data, or crew helicopters, which are expensive, which have personal risk and we have emissions, but they capture high-resolution digital data. So what about drones? How about all these companies? Well, the issue with these companies is that they have a regulatory barrier. They are legally limited to fly on the visual line of sight. That means 500 meters. And consequently, they are much more expensive than helicopters. They are twice the cost of helicopters, and consequently, they are only rarely used. So we are here speaking about how artificial intelligence is changing the world of energy, how it's changing the world of operative maintenance of assets. But how can we apply this technology if at the end of the day, almost 3/4 of the power lines are not digitized because they are inspected by on-foot personnel? So that's our goal. We have developed an aircraft that can vertically take off and land from any flat surface, and then it can fly like a plane. It has several patents over the design, and the goal is to replace crew helicopters with up to 94% of cost reduction, without emissions, without personal risk, and enable the mass digitization of power lines. So we have developed the aircraft on the one hand, but on the other side, the main barrier in the sector is the regulation. So we have deployed these alliances through the value chain with regulators, with end users, with technological partners, and with maintenance service providers. Right now, we are working with 95% of the high and medium voltage grid in Spain, because at the end of the day, this is a highly regulated sector, and thus far, the market is still national due to regulations. Anyway, we have achieved the only authorization in Spain to perform long-range flights, and that is a kind of our main value proposition. We are a team of we were 19, but we are hiring more people. Right now, we are 21 team members. Sorry for the mistake, and we keep growing. This year, we are thinking about finishing the year at 25 team members, including tech, management, people with like Carlos Castellano, the CTO of the company, with the author of 20 patents, the Professor Jesus Villadangos in the software development, myself, Carlos Padilla, in the management and business development sector. I'm MBA, I'm the CEO of Fubex. And the milestones we have achieved so far is that we have achieved the only Spanish authorization. We have achieved a contract of 1 million euros in sales after a lot of time. We started the company in 2015, and since then we have achieved the authorization in May. So you have the idea of the complexity of the sector. We have achieved over 2 million euros in funding, and we have 3 patents. Right now we are attacking the market of infrastructure, concretely the niche of power lines, which is over 200 million euros. But our goal is to be able to provide solutions for the acquiring data, aerial data. So what is the challenge we are facing in this project? Well, to inspect power lines, you need 3 types of data. LiDAR data to generate a digital twin model of the infrastructure. You need thermal data to detect hotspots, and you need high resolution visual data. Visual data is probably the most requested, the most problematic data, because you need very detailed images to detect defects, such as the cotter pins or the conductor strands. That need resolutions below 0.5 millimeter per pixel. So this is very difficult to acquire from the air. In case of helicopters, they can carry a heavy sensor such as the phase 1 gyro stabilized. That means 150 megapixels with 3 kilograms per camera. And even though they have these big payloads, they usually achieve 2 millimeters per pixel, so they are not able to detect all the faults there are. So what is the challenge we are facing? And that is the specific challenge of this project. That the small drones like ours, we cannot have on board such heavy payloads. In our case, we can only carry 500 grams in RGB cameras, and consequently, the image quality is not the same as helicopters. That is very intuitive. If you carry 1 kilogram, 3 kilograms in payload, is not going to be the same as 500 grams. So, what is the solution? If we have tried in this project super resolution. So we have used generative adversarial networks to duplicate the number of pixels in an image, and on top of that, to eliminate the motion blur, we have used the blur gun and real SG gun. And as you can see here, the results are quite interesting, we think, because here you can see the original image, and here use super resolution, and you can see that the resolution is much better. So with this, we have achieved that the resolution, we have double the number of pixels in each image. We have eliminated the emissions, because with this quality of imagery, we can replace helicopters. We are able to increase the price 7.9%, and the flight height which is related with the safety of the aircraft. As long as the flyer you high, the safety, the safer the operation is. We are able to increase the number of meters in 12 meters. So what are the next steps? We have tested this solution in 200 kilometers in inspection, but we want to scale up the solution to be able to inspect over 1,000 kilometers, and the next year we would like to inspect over 10,000 kilometers with this technology. We want to continue improving quality and to find new solutions to be able to adapt this technology to other type of power lines. We want to include the super resolution in all our inspection processes, and we want to research in the use of super resolution in thermal images, because they are the ones who need it the most right now, because the resolution is very low, because the payloads that are available in the market are uncooled in the sector, in the drone sector, the ones we can carry, and super resolution, we think it could be a very good solution. So on top of that, I would like to thank the I-NERGY for giving us the opportunity to develop this technology, and we think that it is very interesting for the future of power line inspection with long-range drones. Thank you.
Thank you very much, Carlos, and thanks for all the good discussions, communications we had all this time. I don't have many questions because I was your mentor, so we have talked a lot of things, like, and it's good to see also drones to be used for good.
Yeah. We are not only drones are not only in the Ukraine doing things. We think that they are going to be key in the deploying artificial intelligence. because at the end of the day, our experience is working with clients. You think that power line companies, they know exactly the type of power line, they know exactly all the data, they have all the data digitized, and at the end of the day, that is not true. So if we want to enable the deployment of artificial intelligence, we need solutions to be able to digitize these infrastructures. And we think that drones, specifically our drones, hopefully, are going to be key in this task.
Great. Any questions from the audience? No, I guess most of people are tired also after so many presentations, but your presentation was great, and also the contribution that you have done, and thank you also for this.
Thank you.
So we reach at the end of this final event. I would like to thank all the teams for the great presentations. And I would like to tell you basically two things. The first is that things don't end with the first technology transfer program. I see that as the beginning of a community that we can build. AI on demand is still on its infancy. It's just building. And the idea is that we become a community that we can help each other in many aspects, both on the technical, the expertise exchange, the stakeholders and networking that we have. As you have seen, a lot of companies here have mutual interest on each other. So how we can become more than the sum of the individuals, sum of the parts. How we can help each other with even publications, with joint events, some surveys. So from my part, I see us as a community that it is in its beginning. Some of you, regardless if you are willing to apply to the second open call, which I definitely encourage you, all of you, to apply. But it goes more than that. And my second point is that AI in demand, as you have seen, it's still in an early phase. There were some issues. We are still solving some of the issues. For instance, for the metadata, we are in contact with the team that are solving that. But in the end, what the Commission wants you to know, and what the AI on demand team wants you to know, that it's the AI on demand. It's a platform that they want not to be linked to a specific individual or organization or specific people. So AI on demand will belong to everyone. So you are also contributors of AI on demand platform now. So you're already part of this community. And as far as I can see, also I-NERGY is one of the most prominent projects so far, with great contribution already in the platform. And this is something that you can capitalize also in your next steps to be in contact and connect, and to make this community even larger. So this is the idea, and this is the overall vision. So, for instance, I will come back and get some feedback from you on the question I did also to Veronica, how we can improve AI on demand, how we can, what features you would expect, how we can better, what things we can put here in order for the SMEs and startups in Europe, but as well as all the, as well as the users, the pilot users can benefit and help you also grow as companies. So that's it. I don't know if anyone wants to discuss something else, or Thomas, do you have any remaining comments? No?
No, I'm fine. Thank you. Also to thank everyone for the presentations, and to remind you of the second open call. There's nothing else to add, and anything you need, you know where to find us. Thank you.
Okay, thank you. Have a nice afternoon. Bye-bye.
Thank you, everybody. Bye.
Bye. Thank you.
Bye. Bye. Thank you. Bye.
Bye-bye. Thank you.
Thank you very much. Bye.